All right, video number 2 for MT225. This is a problem I had up on the board during our practicum session last Wednesday night, and that I promised in my email I would send out a solution to. I figured it's a little more instructive to do the solution by video rather than taking the time to write it up in the same format I do with our homework assignments. So let's take a look at the problem. It's another truss problem to be solved by method of joints. So there's the truss there. Now, this kind of truss we've got set up with our supports in maybe different locations than you're used to seeing. Usually we see one support on one end, one support on the other, but the supports can be anywhere. And that was part of the lesson of the 2 problems I had on last Wednesday's practicum. So here we've got our roller support in the middle, and that's okay. The pin support and the roller support will hold that truss even though we have this cantilevered section, a section that is sticking out beyond the support, and that's okay. We analyze it exactly the same way. Now there are a lot more joints than we have had in other truss problems, but we'll find that several of these members are going to be unloaded. And we'll be able to, by picking the right joints to go to, in solving our method of joints, we'll be able to make pretty quick work of the problem. So first, let's solve the external problem by drawing our free body diagram. So in our free body diagram, we're going to have the truss repeated again. But we're treating the truss as essentially a solid object. We are not worrying about the internal structure at all. All we have to worry about are the external forces, the fact that that pin support supplies 2 forces, RAX and RAY, and that the roller support supplies a single force, and that we have these 2 external forces. We have the 5 kips pulling to the right, and we have 20 kips pushing down. Those are all the external forces. We'll figure out the internal forces, the forces on the members, when we look at the actual joints. So let's do our external problem. This is a non-concurrent force problem, so we have 3 sums that we can work with: the sum of forces in the x direction, the sum of forces in the y direction, and the sum of moments about a point. For our sum in the x direction, looking through the truss carefully, we've got RAX to the right, and we can define our coordinate system to make sure we're clear on our directions for positive. X is positive when it's to the right, Y is positive when it's up, and counterclockwise moments are positive. So a force in the x direction, we've got RAX, and that's to the right, so it goes into the sum as positive. The only other force in the x direction is this 5 kips, and that's also to the right. So we'll put that in as a +5. In the y direction, we've got RAY up, so a positive RAY. We've got RBY up, so a positive RBY, minus 20 kips, because that 20 kips is pushing down. And then we've got to find our moments, and in order to find the moments, we need to pick a pivot point. And joint A is, again, not a bad choice to pick. One of the supports always works out to be a good place to pick your pivot point. A works out nicely because it means that RAX and RAY will generate no moment. We're only going to have moments from 3 forces. RBY has a moment, the 5 kip force has a moment, and 20 kip force has a moment. So let's work each of those in turn. Let's take the 20 kip first. That 20 kips has a line of action that is 5 feet away from A. So its arm is 5 feet times 20 kips. The 20 kip force acting alone would cause everything to rotate clockwise, and clockwise moments are negative. So we have a negative 5 feet times 20 kips. For RBY, we have the same arm, 5 feet, but the force is now RBY, and RBY acting alone would create a counterclockwise moment. So that sum will go in positive. And then we've got the 5 kip force. Be really careful when figuring out the arm for horizontal forces. We're used to the vertical forces and measuring horizontally to get our arms. The key thing to keep in mind is that the arm for any force is the perpendicular distance between the pivot point and the line of action for that force. The line of action for RBY, for example, is this vertical line right here. And the perpendicular distance, the distance measured 90 degrees to that line, is 5 feet from A. Don't make the mistake of saying that 5 kips is 10 feet away. It's not. While it's applied to a point that is horizontally 10 feet away, it's vertically 5 feet away. And it's that vertical distance that matters. The line of action of the 5 kip force is that horizontal line right there. That distance between the pivot point and the line of action, measured at a 90-degree angle, that's 5 feet. So we have a 5-foot arm for that 5 kip force. Acting alone, if we pin the force at A and pull with the 5 kip force, that would cause a clockwise moment, and clockwise moments are negative. So there we've got our sums. Now, if this truss is in equilibrium, the sums add up to 0. So that gives us a set of equations we can solve. So let's shift this up a little bit so we can solve those equations. Going to the x direction equation, we've got something relatively easy to solve. We subtract 5 from both sides, and that'll tell us that RAX equals negative 5. And don't forget your units, since all of our forces are in kips. In this problem, we'll use kips. Now, something important to notice here. This came out negative. That means that we assumed the wrong direction for RAX. I assumed in my free body diagram that RAX was to the right. The fact that it came out negative tells me that my assumption was wrong, that I should have assumed it was to the left. So that just means that I've got 5 kips to the left. So up here in my summary, which I'll scroll to a little bit later, I'm going to write RAX is 5 kips to the left. And I'm going to use left pointing arrow to represent that. The y direction equation we really can't solve just yet because we don't know RAY or RBY. But we can solve the moment equation. Let's run the numbers on it first here. Negative 5 times 20 is negative 100 plus 5 RBY minus 25. That equals 0. If we combine the numbers, we get 5 RBY minus 100 minus 125 is minus 25 is 125. That equals 0. If we add 125 to both sides, we get 5 RBY is 125. And dividing both sides by 5, RBY comes out to be 25. So RBY, 25 kips. And that is positive. So our assumed direction for RBY is correct. So I'll add that to my summary table. RBY is 25 kips up. Now that we know that RBY is 25, we can go back to our y direction equation. So we had our x direction, we had our moment equation, now we've got our y direction equation. The y direction equation says that RAY plus RBY minus 20 equals 0. Well, if we plug in that RBY is 25, we have RAY plus 25 minus 20 equals 0. So if we solve that, 25 minus 20 is a positive 5. Subtracting 5 from both sides, RAY comes out negative 5 kips. That means that our assumed direction for RAY is wrong. We assumed that the reaction at A had to point upward, pushing the truss up. But in reality, it's got to pull downward. That's the effect of this 5 kip force over here. This 5 kip force is trying to rotate everything around B, and that's causing this end of the truss to try to rise. The support has to pull down to keep the truss from moving. Think about this kind of like a long diving board. You've got two supports, a pin on one end and a roller in the middle. Somebody stands on the end or pulls on the end. The pin support has to pull down to keep everything from rotating around B. It'd be even worse if I had a force pushing down out here. So RAY should be 5 kips down. So I'll write that in my summary up here that I'll show you in just a second. So scroll back over here. There's my summary in the upper right corner. I've got my reaction forces from the external problem. RAX is 5 kips to the left. RAY is 5 kips down. And RBY is 25 kips up. So there's our external problem. So let's line that out. Now our goal in the end here is to be able to fill out a table showing what each of the members experiences as a load and whether that member is in tension or compression. Now we've got to count up how many members we've got here to be able to write up our table. Here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 members. So that's a pretty intense truss. There's lots of members to deal with there. We've got 9 rows in our table. So let's write up the table here. We need to know how much load there is in kips and whether or not we've got tension or compression. And we need enough space for 9 rows. Couple more. We got to label out our members, and I like to just go in alphabetical order, so I'll start with A. Now A connects to B, E, and F, so I'll have A, D, A, E, and A, F. No more at A, so I'll go over to B. B connects to A, but we've already got that. We've got BE, BC, BD. So BC, BD, BE. And then we go over to C. We already got BC. We need CD. At D, we've got DE. And then at E, we've got EF. So there we go, all 9 members. So that's what we're going to want to fill in here at the end. So we figured out the external problem. We know what's going on outside the truss in terms of its supports. And it's not a bad idea to be really clear about this at this stage before you jump into the truss and start working on the joints. Redraw this free body diagram over here, but fill in the right directions and the right sizes for your reactions. So I'm going to do that here. I've got the original truss, external forces, 20 kips and 5 kips. And then, according to my summary here, I had 5 kips to the left and 5 kips down. And I had here at B 25 kips up. That way we've got a good look at what's happening at each joint, filling in all the information that we've got to this point. That'll help us in making our free body diagrams of the joints. So in method of joints, once we've figured out the reactions, we need to look at the truss on a joint by joint basis. But remember that at a joint, we can only handle 2 unknown quantities. Now, your initial instinct is probably to try to start at A, but there's a problem with A. Although we've got 2 known forces acting at A, we have 3 unknown forces. We can't handle 3 unknowns at a single joint. We can only handle 2 unknowns. So you might say, well, okay, I can't do A, so go over to B. Well, B is even worse, because although we have 1 known force, we've got 4 unknown forces. D and E are the same. We've got more than 2 unknowns. The only viable places to start on the analysis of this truss will be at joint C and joint F, because those are the only ones that have 2 and exactly 2 unknown forces. So let's start at C. So we'll draw the free body diagram of joint C. So we'll label that here, joint C. And I'll scroll up a little bit here to bring more of it into view. So joint C, it's right here. Draw that little bubble around joint C. Anything that crosses that bubble needs a force in the free body diagram. So we've got 2 forces here. We've got the force due to member BC, which I'm going to assume is pushing joint C to the right. Sometimes if you're not clear, or not sure what the direction of the force will be, just take a guess. It doesn't matter really in the end. The math will tell you if you guessed wrong by giving you a negative answer. Negative answer just tells you you've got your direction wrong. Then we've got joint or member CD. And I'm going to assume that member CD is pushing down. And that's it. Now at a joint, we have a concurrent force problem. So the sum of forces in the x direction and the sum of forces in the y direction are 0. So let's work them out. Sum of forces in the x direction, we have FBC and nothing else. The sum of forces in the y direction, we have a negative FCD and nothing else. In equilibrium, those sums must be 0. It's the only way we can have equilibrium is if the sums of forces equal 0. Well, that gives us immediately what our values must be for members BC and BD. Since those are the only forces acting in the x and the y direction respectively, and those must be 0 to be in equilibrium, each force must be 0. The only way this picture could be in equilibrium if those forces were 0, because there are no forces to counteract them. That means that member BC and member CD both carry no load. You might ask, well, why bother having them in the truss at all? Well, under this particular situation, they aren't doing anything. We could actually delete them. We could cut them away from the truss and not have any problem. But there might be other loadings where those truss members are important. Those are 0 whenever there's no load applied at C. But if we happen to be able to apply a load at C, that will change the loading in members B, C, and CD. So just because a member shows up with no force doesn't mean it will always have no force in all the possible applications of that truss. So let's go back to our table here now that we've figured that out. Member BC carries no load, so we can put that in there. And if a member carries no load, you can't really say whether it's in tension or compression. Member CD also carries no load. So that's the analysis of joint C. Now, if you got the idea down here with joint C, you might see that joint F is going to work out basically the same way. At joint F, we have two unknown forces. One's either pushing or pulling up or down. The other is pushing or pulling left or right. When we draw the free body diagram, we're going to end up with something like this, which means that member AF and member EF will also have no load. So we can fill that into the table as well. So right away, 4 out of our 9 members have no load on them. That also helps us out as we move on to some of the other joints. For example, if we go back to joint A now we only have 2 unknown forces because member AF doesn't have a load on it. We already know what that is. We can essentially remove it in the free body diagram. All we've got as an unknown would be member AE and member AB. So in drawing the free body diagram of joint A, we're only going to have 2 unknown forces. We will need that angle, but fortunately that angle is not too hard to find out. If we use this right triangle here and notice that we've got 5 feet up and 5 feet over, inverse tangent of 5 over 5 is going to be 45 degrees. So the angle's not too bad to worry about. So let's do the analysis of joint A. Now, unfortunately, I'm going to have to go on to another sheet of paper here for this, but try to make it as clean as possible. So let's start on this one here. We'll start joint A here. Maybe I can fit that on the page, but we'll have to go to the other page for another joint. So joint A, let's draw the free body diagram. So we're looking at that right there. We've got, it looks like 5 forces, but we already know AF is 0, so I wouldn't even draw it in there. We've really only got 4 forces. 2 of them we definitely know. We've got 5 kips pulling down, and we've got 5 kips to the left. The other 2 forces we don't know. We've got the force due to member AB, which I'm going to assume is pulling to the right. And then we've got this force due to member AE, which I'm going to assume pulls up and to the right. And has that angle of 45 degrees. So we've got our 4 forces there. We don't have to draw anything in for AF because it has no load. So same as at joint C, do the sum of forces in the X direction and sum of forces in the Y direction. In the X direction, we've got 5 kips to the left, so -5. We've got all of FAB to the right, so plus FAB. And then we've got a piece of FAE to the right. So we've got FAE, it's the horizontal piece or the adjacent piece. Adjacent goes with cosine. In the Y direction, we've got 5 kips down, right there. And then we've got a piece of FAE up. So we have FAE sine 45 degrees. To be in equilibrium, those two sums have to equal 0. We can't quite solve the x direction equation just yet, but we can solve the y direction if we add 5 to both sides. We get FAE sine of 45 equals 5. Divide both sides by the sine of 45. And FAE has a value of 7.0711 kips. So FAE came out positive, which means our assumed direction is correct. And that'll be important in a few seconds when we figure out whether this is in tension or compression. Now that we know AE, we can go back in and figure out what AB has, or what value we have for AB. So let's go on to another sheet here. The sum of forces in the x direction, we had -5 plus FAB plus 7.0711 times the cosine of 45 degrees, and that equals 0. So if we take 7.0711 times the cosine of 45, that gives us 5.0000. So we have -5 plus FAB plus 5.0000 equals 0. And here I'm keeping 5 sig figs in the calculation. That'll give me enough to have 3 good sig figs in the end for my final summary. You have -5 plus 5, that's 0. So FAB ends up being 0. Member AB in this loading doesn't carry a load. So let's go back to our table and fill in what we know. Member AE carries a load of 7.0711. So member AE, 7.0711. We have to figure out whether that's tension or compression. Well, the way to figure out tension or compression is to look at the force in relation to where the member is. So if we look at joint A is right here. Member AE is up and to the right. So I'm going to sketch that in kind of like this. Member AE is up and to the right. Joint A is being pulled toward the middle of member AE. And we saw in the first problem video that I did that if the joints are being pulled toward the middle, that's a sign of tension. Member AE is in tension because it's pulling the supports in toward the middle. It's trying to shrink back to its original size. So it's pulling those joints inward. So member AE is in tension. So we can check the box there. Now we found out that member AB carries no load. So we can fill that in, no load, and no tension or compression. So now we're down to 3 members left. And only one member so far is carrying any load. Member AE is carrying 7.0711 kips. So let's go to joint B. Now at joint B, I've got 4 members connecting there, plus I've got this 25 kip force. Member AB, however, doesn't carry a load. Member BC doesn't carry a load. So what I've really got here are only 3 forces. I've got 25 kips pushing up. I've got some force from member BE and some force from member BD. So let's draw the free body diagram for that. So free body diagram for joint B. So here's joint B. We have a 25 kip force pulling up. We've got some unknown force due to member BE. And I'm going to assume, just for clarity, that that is pushing down, because otherwise I'd have 2 forces right on top of each other, and that gets problematic in drawing out the free body diagram. So I'm just going to assume member BE pushes joint B down. And then I've got member BD. Member BD, I'm going to assume, goes up and to the right. And that one's at an angle, but since the sides are all 5 feet here, the angle's got to be 45 degrees. So there's our free body diagram. I'll try and lay this on top here so that we can keep an eye on the full truss and the free body diagram that we're doing. So there's our free body diagram for joint B. Let's do our sum of forces. So we've got our sum of forces in the x direction and our sum of forces in the y direction. In the x direction, we've got a piece of FBD. We've got FBD and the horizontal component. So horizontal here is the adjacent side. Adjacent goes with cosine. And we have nothing else in the x direction, just that piece of FBD pulling to the right. It's positive because to the right is positive. Then we've got our sum of forces in the y direction. We've got all of FBE down, plus we've got 25 kips up, plus the vertical piece of FBD, that's the opposite side or sine, 45 degrees. So our sum of forces in the x and y directions both must equal 0 in order for the joint to be in equilibrium. If we look at the x direction equation here, that's telling us that FBD times some number equals 0. Now cosine of 45 is 0.70711. It's not 0. The only way you could multiply some number by something that's not 0 and get 0 out of it is if that unknown value is 0. You could also look at it as dividing both sides by cosine of 45. 0 divided by anything other than 0 is 0. So FBD is 0. Member BD is unloaded. In this problem, in the way that we've loaded this truss, member BD does not carry any load. That's good news, because when we go down to the y direction equation, that means this whole term goes away, because FBD is 0, 0 times anything is 0. That leaves us with a much easier equation to solve. Negative FBE plus 25 equals 0, which if you add FBE to both sides, just says that FBE is 25 kips. So member BE carries a load of 25 kips, and it came out positive. That means that we assumed the correct direction. Now, to figure out whether that's tension or compression, we have to look at where member BE is compared to joint B. Member BE is up here above joint B, and it's pushing the joint away. When a joint is pushed away, that's a sign of compression. So member BE carries 25 kips of load in compression. So let's go back to our table and fill that out. So member BE carries 25 kips of force in compression, and we found out that member BD carries no load. So there we are, down to just one unknown, member DE. And the only place we can really go to get member DE would be either joint E or joint D. Now at joint D, there's no force due to member CD because that doesn't carry any load. There's no force due to member BD because it doesn't carry any load. The only forces at joint D are the 5 kip external force and the force due to member DE. So the free body diagram is going to look relatively simple for joint D. We've only got 2 forces. We have 5 kips to the right, and we've got member DE's force, which I'm going to draw to the left. Well, there, obviously, we can't do a sum of forces in the y direction, or at least it wouldn't be very informative. It would just tell us that 0 equals 0. So let's do our sum of forces in the x direction. In the x direction, we've got a negative FDE and a positive 5. And to be in equilibrium, that must add up to 0. Solving that equation, pretty easy. FDE equals positive 5 kips. Now to figure out whether that 5 kips is tension or compression, look at where the member is physically. Joint D is right here. Member DE is to the left. So member DE is over there, and the force due to member DE is pulling to the left. Came out positive, so we know we've got that direction right. The force is in toward the middle of the beam. And when forces are inward, that's a sign of tension. So when a member is in tension, it pulls the joints in toward the middle. When it's in compression, it pushes the joints away. So we've got a joint in, or we've got a member in tension. So we can go back to our table and fill that in. So member DE carries 5 kips of force in tension. So to summarize everything, we draw a summary diagram, which looks a lot like what we've drawn here, except each member will have labeled on it how much force it carries. But before we do that, let's look at how the load is transmitting through this structure. There's some things we can learn here just by looking at what we call the load path. Here we've got 5 kips pulling to the right. Now, if you remember way back here to our external problem, that 5 kips pulling to the right made RAX carry 5 kips to the left. How did it get there? Well, it did it by pulling on member DE, putting member DE into tension. So member DE pulled on joint E with 5 kips of force. Now member EF and AF, they didn't carry any load. The only way that force could have gotten down here was to go through AE. So remember, AE is carrying a good bit of that force. That 5 kip force, part of that 7.0711 kips that AE carries is the force due to that 5 kips. So we've got 5 kips of force pulling on DE, and that pulls on AE, and that's what puts AE into tension. Now, when you take the angles into account, that's where we get that 5 kips of force here, the 45 degrees and 70711. That gives us the 5 kips. So in this case, we're getting a load through down to there like that. That's our load path for that 5 kips getting down to here. The 20 kips, it's mostly being supported on joint B. So 20 of the 25 kips that we've got here are from joint E and the force that's applied to it. The other 5 kips pushing up here is a result of the rotation that this 5 kips is trying to do of the structure around A. So it's trying to rotate the whole structure around A so that B has to push up a little bit harder. So a little bit of insight into where those forces are coming from in the truss. So let's draw our summary diagram and wrap this problem up. Draw the summary diagram. We start out with the drawing of a truss. So let's draw it out like this. Make it a little bigger. Don't really have to put any dimension information on there, but the members and the joint should be clearly labeled. And remember, this is more about communication at this point than about calculation. So you're going to fill in all the letters. Fill in your reaction forces. So we had 5 kips and 5 kips. Make sure those directions are right. We had 25 kips here. We had our 5 kip and our 20 kips external forces. Now going based on our table, let's try and get this arranged so I can put it all in the same place. That'll do. So going based on our table, we can just go down the line. AB carried 0 kips. AE carried 7.07, rounding to 3 sig figs. And it carried tension. Member AF carried 0 kips. Member BC, 0 kips. Member BD, 0 kips. Member BE, 25 kips in compression. CD, 0 kips. We've got DE with 5 kips in tension, and EF, 0 kips. So there's our force summary diagram. Everything that needed rounding has been rounded to 3 sig figs. Everything else is exact. We didn't have to do any rounding to get to those values. So it's okay to leave those as 5 kips. You don't have to go 5.00, things like that. It's really only when you round that you have to worry about sig figs. Here we didn't round to get those reaction forces. We had 125 divided by 5, things like that for our 25 and our 5 kips. So that's a perfectly fine force summary diagram. Only 3 members out of the 9 had any load on them.